Squeeze a gas hard enough and it becomes a mirror. Go ahead, sit with that for a second. I'm not being poetic. I'm not using some kind of dramatic metaphor to get your attention. I mean it literally. You take hydrogen, which is the lightest, simplest, most ordinary gas in the universe. The stuff that makes up the sun. The stuff that floats balloons at children's birthday parties. The stuff we burned in the Hindenburg. God help us. You squeeze it hard enough, and I mean really squeeze, at Checkme's pressures that would make you cry just thinking about them, and it stops being a gas. It stops being transparent and invisible and humble and boring. It turns into something that looks and behaves exactly like a metal. It becomes shiny. It conducts electricity. And yes, it reflects light. It becomes a mirror. Now, I know what you're thinking. You're thinking, come on, Feynman, you can't just squash a gas into a metal. Metals are metals. They've got that particular quality, that particular arrangement of atoms, that whole crystalline lattice business. You don't just compress to that. And that assumption, that very comfortable assumption you're holding right now is exactly what I want to attack. Because it's wrong. And the reason it's wrong is so beautiful that I've been thinking about it for years, and it still makes me smile. Let me back up and tell you something about hydrogen first. Something very simple. You already know hydrogen is the first element on the periodic table. One proton in the nucleus, one electron zipping around it. That's it. The whole atom is almost nothing. In fact, a hydrogen atom is mostly empty space. The nucleus is so small compared to the electron's orbit that if the nucleus were the size of a marble sitting in the middle of this stage, the electron would be about a mile away. The atom is almost entirely nothing. It's an advertisement for emptiness. When hydrogen is a gas, you have pairs of these atoms bonded together into little molecules, H2, two protons, two electrons, behaving like a little family, moving around, bouncing off each other and the walls of whatever container you've got them in. The electrons are tied to their protons. They belong to their atoms. They are, in a sense, domesticated. Under ordinary conditions, those electrons are not free to wander. Now, here's the crucial thing about metals. What makes copper a metal? What makes iron a metal? What makes them shiny and conductive and all those nice things? The answer is that in a metal, the electrons are not domesticated anymore. They don't belong to any particular atom. They roam freely through the whole material. The electrons are shared. They exist in a kind of communal pool, a sea of electrons sloshing around between all the atomic nuclei, and it's this sea of free electrons that conducts electricity, because when you apply a voltage, those electrons start drifting, and it's this sea of free electrons that reflects light. When a photon hits the surface, those free electrons wiggle in response and emit another photon right back at you. That's why a mirror is a mirror. That's why your kitchen knives are shiny, free electrons. So the question becomes, what does compression have to do with any of this? Why would squeezing hydrogen set its electrons free? Here is where I want you to do something for me. I want you to imagine, really picture this, what happens when you start compressing hydrogen gas. In the beginning, the molecules are far apart, lots of empty space between them. The molecules are practically lonely. Now you push them together, closer. Closer, the molecules start bumping into each other more often. At enormous pressures, the hydrogen becomes a liquid. It's so cold and compressed that the molecules are jammed right up against each other, touching constantly, but they're still molecules. The H2 pairs are still together. The electrons are still domesticated. But keep pushing. Push with a pressure of 1 million atmospheres, 2 million, 3 million. And here is where something radical happens. The molecules can't survive anymore. The pressure is so immense that the H2 bonds break. You no longer have molecules, and you just have individual hydrogen atoms, naked protons, and their electrons, all crushed together in an impossibly dense sea. The atoms are so close together, so frantically, violently close, that the electron of one atom starts to overlap with the space of the next atom, and the next, and the next. At this point, There is no longer any meaningful sense in which an electron belongs to a particular proton. The electrons become shared, they become free, they become the metallic sea. The gas has become a metal. Now let me tell you something that will knock you sideways if you're paying attention. This is not just a laboratory curiosity. This is not a party trick performed in some physicist's diamond anvil cell. This is what's happening right now, at this moment, deep inside the planet Jupiter. Jupiter is mostly hydrogen. It's an enormous ball of hydrogen gas, held together by its own gravity, which is crushing the inner layers under pressures that dwarf anything we can produce in a laboratory. At a depth of perhaps 20 or 30,000 kilometers into Jupiter, the pressure becomes so extreme that the hydrogen undergoes this very transition. It becomes metallic. And because metallic hydrogen can carry electric currents, and because Jupiter rotates, you get swirling currents of conducting fluid deep in the planet's belly. And those currents, those enormous rivers of electricity in the metallic hydrogen, generate a magnetic field, Jupiter's magnetic field, the biggest magnetic field of any planet in the solar system. So strong that if you could see it with your eyes, it would appear in the night sky larger than the full moon. And the source of it, the engine of it, is this phase of matter, this improbable mirror made from the universe's simplest gas. Go home tonight and look at Jupiter through a telescope if you can find one. You are looking at a planet with a metallic mirror at its heart, generating a magnetic field that could swallow the Earth. Now, I've been teasing you a little, talking about pressures in the millions of atmospheres, as though we can just go ahead and casually produce such things. Let me tell you about what it actually takes, because this is one of those places in physics where the experimental difficulty is itself a kind of poetry. One atmosphere is roughly the weight of the air above a square centimeter of your skin, standard, normal, comfortable. Now multiply that by 4 million. That's the pressure at the center of a hydrogen column inside a gas gun, or more practically, inside what physicists call a diamond anvil cell. 2 diamonds pointing tip to tip with a tiny sample of hydrogen squeezed between them. Why diamonds? Because diamond is the hardest material we know, and even then, even with 2 of the hardest objects on Earth pressing on a sample the size of a grain of sand, you're still barely reaching the pressures where metallic hydrogen might appear. The diamonds sometimes shatter. The pressures involved are so violent that the tools destroy themselves in the attempt to understand the universe. The first credible experimental evidence that metallic hydrogen had been produced came in 2017 from a group at Harvard. Isaac Silveira and Ranga Dias announced they had achieved it. They had squeezed hydrogen to around 495 gigapascals, which is a breathtaking number, and they had observed the reflectivity change that signals the metallic transition. The scientific community reacted with a mixture of excitement and skepticism, as is entirely appropriate and correct. Other researchers wanted to reproduce it. The sample was lost, literally lost. The pressure system relaxed and the metallic hydrogen, if it was there, disappeared, which is itself a remarkable thing to happen. You make history and your sample vanishes before anyone else can see it. Science is like that. It is an imperfect, human, sometimes heartbreaking process of groping towards something true. The experiments are ongoing. The question of whether metallic hydrogen has been definitively produced in the laboratory and whether it might remain metallic when the pressure is removed, which would be extraordinary, is still not fully settled as I speak. I love that. I love that we're still in the middle of this story. But let me take you back to the underlying physics, because I don't want you to think this is just about one exotic experiment. The phenomenon I'm describing, pressure-driven changes in the electronic structure of matter, is not some bizarre edge case. It is a fundamental truth about the universe. The identity of a material is not fixed. The properties of matter, conductivity, reflectivity, magnetism, transparency, are not God-given essences. They are emergent consequences of how atoms are arranged and how close together they are and what their electrons are doing. Change those conditions enough and you change everything. Let me give you a simpler example to build your intuition. Take sodium. Now, ordinary table salt comes from this stuff. Sodium is a metal at normal conditions. Everybody knows that. It's in every kitchen in the world dissolved in salt. But if you take pure sodium metal and squeeze it to extreme pressures, it becomes transparent, a transparent metal. It becomes an insulator. The pressure changes the arrangement of the electron energy levels enough that the electrons can no longer absorb visible light. And so the metal becomes see-through. The same material, different pressure, opposite properties. Oxygen, which is a gas at normal conditions, becomes metallic under pressure. Carbon, which is either graphite or diamond depending on arrangement, becomes a metal at high pressures. The table of elements is not a table of fixed identities, it is a table of possibilities, and pressure is the dial that lets you turn those possibilities on. Now, I want to tell you something that bothers me in the best possible way. If metallic hydrogen can form at high pressure, and it seems it can, and it is forming right now inside Jupiter and Saturn, there is a theoretical prediction that says metallic hydrogen, if we could produce it and then release the pressure, might remain metallic, might remain in this exotic phase at room temperature and zero external pressure, a room temperature ambient pressure metal made of hydrogen. This would not be ordinary. This would be extraordinary, and not just as a curiosity. Hydrogen as a metal at room pressure would be a superconductor. Almost certainly, according to the theoretical calculations, a room temperature superconductor would mean electrical current flowing with zero resistance. Zero. None. No energy lost to heat. Magnetic levitation without enormous refrigeration equipment. Power grids that lose nothing in transmission. Transformational technology. The reason this prediction has physicists so excited and so frustrated, because it keeps being just out of reach of eyes, that theory says it should be possible. Nature might allow it. We just haven't managed to catch it yet. Here is what I find so philosophically delicious about this whole situation. Hydrogen is the simplest atom. One proton, one electron. It is the atom a student of physics uses when they want to solve something exactly, cleanly, without approximation. The hydrogen atom is the first triumph of quantum mechanics, precisely because it is simple. And yet the behavior of bulk hydrogen under extreme conditions is one of the hardest unsolved problems in condensed matter physics. You can write down the Schrödinger equation for a hydrogen atom and solve it. You cannot write down and solve the Schrödinger equation for 10 to the 23rd hydrogen atoms at 4 million atmospheres. The interactions are too many. The correlations between electrons are too complex. The simplest element in the universe, in sufficient quantities and under sufficient duress, defeats our mathematical tools. This is a recurring theme in physics that I find endlessly fascinating and a little humbling. Simple rules, enormous complexity. You know Newton's laws, F equals ma. Simple. But try to predict the weather. Simple rules, three bodies gravitating around each other. Try to predict their long-term trajectories exactly. You can't. The universe is constructed in a way that allows simple underlying rules to generate complexity that overwhelms even the most powerful computers we will ever build. Hydrogen, one proton, one electron. But put enough of them together under enough pressure, and you get a problem that has been unsolved since the 1930s. Let me go back to 1935 for a moment, because there is history here worth knowing. Eugene Wigner and Hillard Huntington, these are real physicists, real people, published a paper in 1935 in which they predicted that hydrogen would become metallic under sufficient pressure. This was before we had modern quantum theory fully worked out. This was before we had computers. They did the calculation by hand, essentially, using the theory of metals that existed at the time, and they concluded that at somewhere around 25 gigapascals, hydrogen should undergo a metal insulator transition. That prediction turned out to be wrong about the specific pressure. The actual number is much, much higher, closer to 400 or 500 gigapascals, but the essential physics was right. An idea published in 1935, almost a century ago, about a phase of matter that still hadn't been definitively observed in 2017. 82 years between the prediction and the experiment. 82 years. I think about scientists like Wigner sitting in their offices in the 1930s doing calculations that they knew could not be tested for decades, if ever, with the technology available to them. They were writing letters to the future. They were saying, here is what we believe nature does. We cannot check it yet, but we believe in the mathematics and in the consistency of nature enough to write it down and publish it. That is an act of extraordinary intellectual faith. Not faith in the religious sense, faith in the coherence and testability of physical law, faith that if you reason carefully enough from correct principles, you will arrive somewhere real. Let me bring this back down to something physical. So I want to give you a thought experiment that might help you feel the quantum mechanics here rather than just memorize it. Imagine an electron as something you're trying to confine, trying to pin down in a small region of space. Now, quantum mechanics tells us, this is the Heisenberg uncertainty principle, that the more precisely you confine a particle in space, the more wildly uncertain its momentum becomes. The more you squeeze the electron into a small box, the more frantically it bounces around inside that box. Its kinetic energy goes up. Now, in a normal gas of hydrogen, at low pressure, the electrons are confined to regions of space that are roughly the size of atoms, about an angstrom, 100 millionth of a centimeter. This costs some kinetic energy, but it's manageable. There's a balance between the attraction of the proton, pulling the electron in, and the quantum mechanical cost of confining the electron tightly. But here's what happens when you compress the gas dramatically. You force the atoms so close together that the confining boxes, the individual atomic regions, start to overlap. Now, each electron doesn't know quite where its box ends. The uncertainty in position increases, and paradoxically, when many atoms are crammed together and the electron wave functions overlap substantially, the electrons can delocalize and they can spread out over the entire material rather than being confined to one atom. Delocalization over a large volume means the electron is actually less confined, not more. And a less confined electron has lower kinetic energy. At high enough pressure, the system finds that it's energetically favorable for the electrons to delocalize completely, to stop belonging to any particular atom. Because a delocalized electron in a sea of conducting electrons costs less kinetic energy than a tightly confined electron in an individual atom. The atom ionizes itself to lower its energy. The gas becomes a conductor. This is the heart of the phenomenon. And I want you to notice something about this explanation. It is entirely quantum mechanical. There is no way to understand why hydrogen becomes metallic using classical physics. None. If you imagine the electron as a little marble bouncing around inside the atom, the whole argument collapses. The delocalization, the wave function overlap, the uncertainty principle. These are quantum facts with no classical translation. This is one of the great reminders that the world runs on quantum mechanics, and our classical intuitions are just useful approximations that work in a limited regime. Outside that regime, very, very small scales, at very high pressures, at very low temperatures, the world is genuinely, irreducibly quantum mechanical. And it is strange. It is stranger than we tend to admit when we're being comfortable and professional and careful. Let me be honest with you about how strange it is. An electron in metallic hydrogen doesn't have a position. It doesn't live in a specific place in the material. It is smeared as a mathematical wave across the entire chunk of material. Its presence is statistical, probabilistic, spread out. When you pass electricity through metallic hydrogen and when you apply a voltage, you're not pushing individual electrons from one end to the other like marbles in a pipe. You're causing this delocalized quantum sea to shift, to flow, in a way that has no precise mechanical description. You get current, observable, measurable, useful current from something that we can only fully describe with wave functions and probability amplitudes. The classical picture of current as marbles flowing through a pipe is totally wrong. It works and it gives you the right answers for engineering purposes, but it's wrong. The actual story is quantum mechanical, non-local, and almost impossible to visualize without giving up on classical intuition entirely. And if metallic hydrogen is a superconductor, which theory strongly suggests it would be, then the story gets even stranger. In a superconductor, electrons pair up into what are called Cooper pairs, quantum mechanical partners that move through the material without any scattering, without any resistance in a macroscopic quantum state. The entire current-carrying population of electrons enters a single quantum state that spans the whole material. It's not that each electron somehow avoids bumping into things. It's that the paired electrons are in a collective quantum state that is topologically protected from scattering, macroscopic quantum coherence, the quantum weirdness you normally see only in individual atoms, playing out across an object you can hold in your hand. It is one of the most bizarre things in all of condensed matter physics, and we understand it with Bardeen, Cooper, and Schrieffer's theory, BCS theory, which is a triumph of 20th century physics, but understanding the equations of it doesn't make it any less strange when you really sit with what it means. So we have this gas, hydrogen, the gas that makes up most of the visible matter in the universe, the gas that powers the sun through nuclear fusion, the gas that first formed in the early universe minutes after the Big Bang, and under the right conditions, this gas becomes a mirror, becomes a conductor, becomes perhaps a room temperature superconductor, the humblest atom, the simplest electron configuration. And it leads us to the hardest unsolved problems in physics and to the interior of planets and to technological possibilities that could reshape civilization. I want to say something about why I think this matters in a way that goes beyond the specific physics. People sometimes ask me why physicists spend so much energy on things that seem remote and impractical. Metallic hydrogen, Jupiter's interior, diamond anvil cells. Isn't there more urgent work to be done? And I want to push back on that question, not because practical work isn't important, but because the track record of pure curiosity-driven physics is extraordinary. Nobody working on electromagnetic induction in the 19th century was thinking about power grids. Nobody who developed quantum mechanics in the 1920s was thinking about transistors and smartphones. Nobody who worked on nuclear physics in the early 20th century was thinking, well, some of them weren't thinking. But the point is that fundamental knowledge about how nature works has a way of becoming eventually the foundation of practical technology. Room temperature superconductors would be world-changing. The path to them runs through understanding metallic hydrogen, which runs through understanding quantum mechanics and the theory of metals, which began with people who just wanted to understand why metals were shiny. Curiosity is not a luxury, it is the engine. But I don't want to argue for curiosity purely on practical grounds, because that's not really why I love physics. I love physics because the universe is surprising, because every time I think I understand how matter works, every time the picture seems to settle into something comfortable and comprehensible, something like metallic hydrogen appears and says, wait, you thought you knew what hydrogen was. You knew one proton, one electron. Simple. But here's what it becomes at 4 million atmospheres. Here's what hides inside the comfortable ordinary description. Here is the stranger truth underneath the familiar face. Matter has no fixed identity. A gas can become a mirror. The stuff of birthday party balloons can become the engine of a planet's magnetic field. The simplest atom in existence, squeezed hard enough, becomes a room temperature superconductor. Maybe, if we can figure out how to hold it there. The universe is not required to make sense to us. It is not obligated to be simple or kind or comprehensible on our terms. And yet, and this is the thing that keeps me up at night in the best possible way, it turns out that with enough effort, with enough mathematics and experiment and creative imagination, we can understand it. Not perfectly, not completely. There are still profound unsolved questions about metallic hydrogen, about the exact phase diagram, about whether stable metallic hydrogen exists at ambient pressure, about the precise mechanism of superconductivity in such a material. I don't know the answers to those questions. Nobody does. And I am not embarrassed to say that. In fact, I want to say something even stronger than that. The most exciting phrase in physics is not eureka. It's not even I found it. The most exciting phrase is we don't know yet. Because we don't know yet means the game is still on. The universe is still hiding something from us. And there is still work to be done, still experiments to run, still predictions to make and test and argue about and revise. Hydrogen is the first element. It makes up about 75% of the ordinary matter in the universe by mass. We've had it around since 10 seconds after the Big Bang. It makes up the sun. It makes up Jupiter. It floated that doomed dirigible across the Atlantic. We've used it in rockets. We've studied its spectrum and used it to build quantum mechanics. We thought we knew it, and now we squeeze it hard enough and it looks back at us. That's the thing about the universe that I find most astonishing, most humbling, most wonderful. No matter how long you look at something, and no matter how carefully, how cleverly, how lovingly, there is always another layer underneath, always another surprise waiting at the next decimal place, or the next order of magnitude in pressure, or the next degree of temperature. The universe is inexhaustible in its strangeness. So the next time you fill a balloon with hydrogen, or you look up at Jupiter hanging in the evening sky, or you read about room temperature superconductors in some news article and roll your eyes at the hype, I want you to remember this. Somewhere inside that gas, at the right pressure, there's a mirror waiting to form. There's a metal waiting to appear. There's a phenomenon so bizarre and so beautiful that it took 80 years just to go from the prediction to the experiment, and we're still not completely sure we've caught it. The gas that becomes a mirror when you squeeze it hard enough, what else is hiding in plain sight?